the next talk in the session, which is our very own Carl Hibbitts. So what we don't know about water ice on the moon and a concept for how to fix it. So tell us how to fix
Thank
it,
you.
Carl.
All right, so there actually isn't that much we know about water ice on the moon, and that is the crux of implementing a resource evaluation campaign. And the question I try to address here is not exactly how are we going to answer it, but what are the steps, what are major characteristics of what do we need to know, and in general, how well can we do it? How well do we need to do it, and how potentially can we do it? All right, basically, as Laszlo mentioned, currently we have very, very coarse understanding of water ice on the moon, and we need to get down to, meter scale. How do we do it? Right, that is what I try to address here in some detail. I want to start first with what do we need to know, and Laszlo went over a lot of this, but it's always useful to hit upon. And I was happy to hear very similar numbers from him, not exactly the same, but that's fine. So we need to understand the location and abundance in the subsurface because water ice that's going to be a reserve is going to be in quantity in the subsurface to about 10 meters in X and Y within the upper meter. And upper meter is what I think we need to limit to because that is what the current technology is being developed to extract. And while we may have water ice down, deep water ice, if it's not extractable, then it's not a useful reserve. Again, economically viable amounts of it is, a couple percent, few percent level, which means, like Laz said, also we need accuracy about 1, or I put 0.5%, fine. And no need to know the vertical distribution if we're limiting to upper meter anyway, just dig it all up and extract it. Now, it's also very useful for modeling purposes. Again, Laszlo pointed this one out, to understand the location abundance on the surface to similar levels, so we can try to tie the surface signatures to near surface abundance via modeling, such as we will get from Viper and other missions. This is very important to do. And we need to understand the physical state, so we understand what kind of a technology that we actually need to deploy to extract, mine, and process water ice. Is it indurated or is it ice-coated grains, granular, or whatnot? And Kevin Cannon gave a great presentation on the various options that may exist down there. Okay, very important. Finally, the composition. Not that it's water ice, but what else is in there besides water ice? We need to understand whether the Cabeus results are applicable to everything on the moon. And if we detect it anywhere, then I think we'd have to argue that it's possible everywhere. And so we need to plan for that, even if we don't want to measure it any further. So we need to understand location, physical state, and abundance. So what do we already know about this? Well, really not a whole lot, right? We don't know that there really is ice there unless in other than Cabeus crater. Our current understanding of water ice or water concentration is largely from neutron spectroscopy data, which is at the 40 kilometers per scale. The Lunar HMAP is going to get us down to 20 kilometers or better, and that will potentially start to resolve some PSRs, and we might be able to then infer some higher concentration true ice deposits. Right now, the average abundance of water in the PSR is about 100, in the polar regions is about 150 ppm. Is it concentrated in water ice and PSRs or not? We think it is, but that's what prospecting is about. We know that there is some surface ice, possibly frost, but the signal noise is pretty bad. However, we should assume that KPLO and Lunar Trailblazers will be successful, and they will get us respectively 2-meter morphological images and 100-meter compositional images. And the Trailblazer stuff will also include robust measurements of water ice grain size, which can be very useful for inferring processes. Physical state, we do know this from radar, that it's not likely contiguous layers. We don't see that radar reflection. There are some scattering areas in the bottom of some craters. They don't necessarily correspond to high thermal neutron areas, so it's kind of not certain what they mean, but we do know there's not huge sheets of water ice in the upper meter at least, okay? And Cabeus results do suggest our model to be granular. And we also know from Cabeus a lot of contaminations in there. And finally, we have to have good modeling that Laz also pointed to, so we can link near surface water to surface expression, so we can understand where we really want to go. So what more do we have to know? Well, basically, I just said what it is. We need to get a location understanding down to a few meters from where it is right now. From orbital measurements, we can't get there, but we can get closer than we are now. Maybe Lunar HMAP is close enough, and I'll talk to that in a bit about the high resolution observations, whether it's radar or neutron, for understanding near surface water ice. As I mentioned before, location, we're going to get that pretty good for the near surface, right? And I think I mentioned composition already. Again, I would assert that if we find contaminants in any of the water ice that we considered for prospecting, then we have to design for it and everything. And then maybe we don't have to measure it anymore. We just have to design for its presence. Okay. All right. So how do we go from this, which is a image of the South Pole, as you recognize, with PSRs outlined and the potential Artemis landing sites. We don't understand water ice any better than maybe the bigger squares there, and I should say water concentrations. And yet we need to go down to this, which is see in the right-hand side. Something about that size would probably constitute a reserve. As Laszlo said, we actually need something less than that for 15 meters per, for 15 metric tons per year, but a sustained presence may require up to 100 metric tons, as we derived from this supply and demand workshop a couple years ago. So we start with this, and then these just 10-kilometer diameter circles on ridges that are adjacent to PSR are saying, okay, so these are the areas of real interest, right? Because this is the area where the rovers can potentially get to and bring the stuff back to the surface. And I want to point out that Julie Kleinhetz in Ascend 2020 did a great job beginning to look at this, and I'll show a picture of it soon. And she is presenting a much more refined, mature version at Ascend 2022, so I encourage you to see that presentation. And speaking of which, this is extracted from the 2020 presentation, showing that, we will start at a ridgeline somewhere and go a few kilometers in there. So the areas of real interest we have is within a few kilometers of the ridgelines in PSRs, or within a few kilometers of nearly permanent eliminated areas. So we don't need to actually map at 5 meters or 10 meters the entire PSRs of the South Pole. We just need to map the ones that are accessible. So how do we start to get there is a question. Right now we're at 20 kilometers per pixel about, if Lunar HMAP works. If it doesn't, but it should, but if it doesn't, we're at like 40 still. But with even lower altitude observations, whether one uses a neutron and other things that control the periapsis, we've done at APL some studies that show we can get down to 5 kilometers above the terrain. And that's shown right here and here and here and here. So potentially we can get between 5 to 10 kilometers space resolution of whatever for subsurface measurements, which is potentially really nice, because that moves you from, let's say, 40 kilometers per pixel, which is 1,600 square kilometers, to just 25 square kilometers. That might be tractable for roving or putting down impactors for sampling the the surface, for then following up with that information. So let's pretend this is where we start. Then after a whole bunch of low altitude measurements using some technique, we find one area that looks good, because we're going to plant our flag here, or somebody will, and we have access to there. So what do we do next? So
2 minutes, Carl. 2 minutes.
Thank you. Perfect, Clive. Thank you. So this is a blow up of that region. Saying that, here, let's just say we had some orbital information that had low abundance, medium abundance, high abundance, and we have a godlike knowledge, but we don't. But this is where the reality is. We don't know it yet. How do we find that reality? Well, one thought is you put a lander in there, of course, and perhaps you can put out rovers. Quick look at the rover technology that's pure battery powered, because I don't think RTG is going to work for, let's say, 10 different rovers, or one very expensive rover, not in the near term. Battery only isn't going to get you more than maybe a kilometer at the most. And so 5 kilometers pixel still isn't tractable to a battery only rover. Well, maybe we can use impactors like that. That take a lot of impactors. That one got lucky, but that could work as well. I don't know what the answer is, and we need to figure out what that answer is, so that afterwards one could potentially then put down a rover that will be able to have greater capability and go over the area that was found to be actually rich in water ice. So it's going to be a multi-tiered effort, is the point. We start, as actually Laszlo said, orbital measurements, then ground-based. Let's go and recon out and just find generally where the reserve is, and then a more detailed assessment of that. So that's what we think the process needs to be. Exactly how we do it, well, hopefully that's what we can leverage 17 for and talk about here at 18 from a programmatic perspective, how to accomplish this multi-tier effort. So the question I have for everybody here is, how do you see yourself fitting into this prospecting architecture or something like this? How did your company, your institution fit in this? And what are these non-technical challenges jump out at you to implement this similar campaigns? What do you need to know et cetera, et cetera. So I'll just leave this up, Clive, and I think I probably have about a minute left. No, actually, I'm done. Thank you very much.
Perfect timing, Carl.